Have you ever dreamed of hitting print on your 3D printer and then a few hours later just pulling a fully interactive smart object right off the build plate? I mean, no assembly required, no wires, nothing. Well, that dream of true desktop manufacturing, of creating custom smart devices right in your own home, it's a lot closer than you might think. So let's get into how this actually works.
Yeah, what we're talking about here is the ability to fabricate these really complex interactive devices, like these awesome little gadgets that can actually sense your touch and have them come out as a single, complete object. This is the whole vision of desktop manufacturing, right? Moving beyond printing simple plastic shapes to creating things that are, well, alive with technology the second they're finished. But, okay, let's get real for a second. Right now, today, if you want to make a 3D print interactive, you are absolutely not done when the printing stops. Oh no, you are just getting started. And that gap between the digital dream and the physical reality, it's often this frustrating, tangled nightmare of post-print assembly.
I mean, makers and designers right now face a whole mess of hurdles. You got all this extensive, messy wiring to try and stuff inside your print. Any touch-sensitive spots? You have to decide on them way in advance, and you can't change them. It takes all this tedious manual assembly, soldering, trying to connect separate electronic parts, which, let's be honest, often leads to connections that just don't work. It's the kind of process that just kills creativity.
So this brings us to the big question, doesn't it? What if we could just eliminate all of that frustrating post-print work? What if the printer itself could handle both the plastic structure and all the smarts all in one seamless process?
And that brings us to the first major breakthrough. You can think of it like giving a 3D printed object its own skin, or maybe a better way to put it, its own nervous system. A way for it to feel touch anywhere on its surface, using a method that is incredibly simple and, frankly, beautiful. The tech behind this is called Swept Frequency Capacitive Sensing, or SFCS. But let's just break that down. Basically, it sends a whole bunch of different electrical signals through a conductive material. When you touch it, your finger actually changes those signals in a really specific way. And by reading that change, a computer can figure out exactly where you're touching. Okay, now this is where it gets really clever. On a normal, fully conductive surface, like that top bunny you see, the sensor gets confused. Why? Because different points can be the exact same distance from the wire, so their signals look identical. But the breakthrough, which you can see on the bottom bunny, is to create a single, unbroken conductive path that literally snakes its way across the entire surface. And here is the absolute genius of it. With that single stroke path, every single point on that object now has a unique distance along the path from the sensor's one and only wire. This means every touch produces a completely unique electrical signature. No more confusion. It is such a brilliantly simple solution to a really complex problem. And the results, they're just night and day. Look at the top. The fully conductive bunny is a total mess. The sensor gets it wrong constantly, accuracy as low as 28%. But then you look at the bottom. The single stroke bunny, 100% accuracy, across the board, perfect detection. This technique just flat out works.
Okay, so our object now has a nervous system. It can feel. But what good is a nervous system without a brain to understand what it's feeling? So that brings us to our second huge breakthrough. A way to print the skeleton that reliably connects that sensor skin to the electronics.
And this is the next major hurdle, right? You've got this amazing, touch-sensitive surface printed directly into your object. But how do you actually connect it to the microcontroller, the brain, without going back to that same old mess of soldering and manual wiring?
The answer is a technique called printed integrated circuits. And the core idea here is to treat a regular off-the-shelf printed circuit board not as something you add later, but as just another material that you embed directly into the object while it's being printed.
The process itself is kind of like this elegant dance with the machine. The printer starts building the object, and then it automatically pauses, leaving this perfect little custom-made cavity. The user just pops the circuit board inside. Then comes the magic step. They call it projection, where the printer actually injects conductive filament directly into the board's holes. And finally, the print just resumes, sealing the electronics inside forever.
And here, if you look really close, you can see why this is such a game changer. On the left is what happens if you just try to print over a hole. You barely get any connection at all. But on the right, with projection, that conductive filament is forced deep into the hole, creating this super solid, totally reliable electrical and mechanical bond. It's like having automated, solder-free wiring built right in.
So we've got a sensor skin, and we have a way to connect it to a brain, and it's all happening right on the printer. So what can you actually do with this? This is where things get incredibly exciting.
Because when you combine these two breakthroughs, the possibilities just explode.
First up, custom interactive toys. I mean, imagine this 3D printed cat. Because the sensor covers its entire body, it knows exactly where you're petting it. So a gentle stroke on its head might make it purr, but a pat on its back could make its little tail wag. Every single surface becomes an input.
Or think about education. This 3D brain model becomes this unbelievable learning tool. When a student touches the frontal lobe, a screen could pop up with info on decision-making. Touch the cerebellum, and a video explaining balance starts to play. It completely transforms these abstract concepts into a hands-on, physical experience.
And this technology can create interfaces that actually adapt to you. Take this pen grip. You could hold it one way, and it selects the paintbrush tool in your design software. But just shift your grip slightly, and you instantly switch to an eraser. The tool is intelligently responding to your own natural movements.
And finally, we can bring data into the physical world. This isn't just a plastic model of Mount Fuji, it's a tangible, explorable map. You can touch a specific ridge and hear about its elevation and its history. You could trace a path with your finger and see the trail light up on a screen. It makes data something you can actually hold and feel.
So what does all of this really add up to? Well, it's way more than just a cool new way to make gadgets. This is about a fundamental shift in what personal fabrication really means for all of us.
You know, the researchers behind this put it perfectly. They said that the rumblings of a revolution in desktop manufacturing are now louder than ever. It's just like how personal computers brought publishing to every single desk. Well, these techniques bring the entire factory to you.
So, the ultimate takeaway here is this. We are moving past printing inert, dead plastic shapes. We are now at the point of fabricating complete, functional, and deeply personalized smart devices in one single automated process. You go from a digital file to a finished product, and all the complexity is handled by the machine.
What this technology does is it democratizes the creation of interactive hardware. It puts the power to invent, to customize, and to build the smart objects of the future into the hands of anyone with an idea. So the final question is a simple one. When this technology is sitting on your desk, what will you create first?